Professor, can you hear me? Professor?
Ivan, can you hear me okay?
Yes.
Great. All right, so let's get started then. So hello, good morning. I hope you guys are all doing well as we head towards our Thanksgiving week next week. Couple quick announcements. So on Thursday afternoon at 5, William is going to do the chapter 4 review, which is posted on Moodle. So if you're interested in attending that, the link will also be in Moodle, and I will send an email reminder tomorrow. For the week of Thanksgiving, so next week, we are not going to have class on Tuesday, and there will be no mini quiz on Wednesday because we're not going to cover anything new on Tuesday. I think I've gotten too many emails from people traveling. So we will cover the first part of chapter 5 on Thursday of this week, and then we won't cover new stuff till we get back from Thanksgiving. So that's our sort of plan moving forward. So today we are going to cover the last 2 sections of chapter 4 in our applications, and then you'll have all the material that you need to study and prepare for the chapter 4 quiz. The chapter 4 quiz is on Monday of next week. It'll be open the full 24 hours as usual. So you'll need to find a 1-hour period to complete that. I think that's it for announcements. So I'm going to switch over to DotCam, and when I do that, I'm also going to hide my live stream video just to try to help the bandwidth for the DotCam to make sure that that's a little stable since we've been having some internet issues. All right, so let's switch over. Go there. All right. So we have 2 more applications to consider as we think about what we've learned about maxes and mins and inflection points. The first applications that we did were last week when we looked at economics with marginal revenue, cost and profit, those sorts of applications. The next one we're going to look at is an application to biology. And so we look at what is called the logistic growth model. So in biology, we often want to model things that are growing. And so these can be things like populations of animals or bacteria or things like that. And so a population grows quickly. There's a lot of factors that we have to consider that impact how it grows. So for example, if you are thinking about modeling the number of penguins that are living on a particular island, right? How quickly they grow and how big they can grow depend on things like how much food is available, if there's any natural predators, how much space there is on the island, right? So all of these things impact how big that population of penguins can become, okay? And so when we talk about a logistic growth model, it has a very specific form, and I want to talk about each of the variables that show up in the model. So this is the general model. So P is for population. And so you'll see that we have an L, a C, a K, and a T. So I want to start with T. T is our independent variable. That's the thing that is changing, and that is time, okay? Depending on what you're modeling, time could be in years if you're talking about things like penguins, right, that take a long time to grow, but it could be hours if you're talking about something like bacteria, right? So it just depends. So time units will be given in the problem most of the time, okay? So this is our independent variable. Okay, so that means all the other letters you see are constants. Okay, so let's talk about each one. So we'll start with L. L is the number that's found on top of the model. It's up here, and it's what's called the carrying capacity. And so the carrying capacity is going to be how large the population can grow. So there is a maximum population for everything on Earth, and that is called the carrying capacity. So we often talk about this by saying something like, how large will the population be after a long, long time, right? Because eventually it's going to get to its maximum population. So that's the carrying capacity, and that is the number found on the top of the model, okay? K is your growth rate. That's going to dictate how quickly your model grows. Okay, the larger your K, the faster you get to your carrying capacity. Okay, so that time is our independent variable. And then we have this constant C, okay? And so this constant C is a number that accounts for all factors that impact the population. Okay, so for different populations, that C is going to be different. But what biologists do is they work to figure out all of the things that are going to impact the population, and they come up with a factor for that particular population. Okay, so again, that's things like predators, availability of food, space, disease, all of those things impact this particular constant. And that is particular to every different population you would ever look at. For our purposes, C will be given as a constant number, but just know that that number was created by biologists for that particular model. Okay, so those are the different factors of logistic growth models. And now I want to talk about what logistic growth models look like. Okay, so they have a very specific shape of the graph, and they look like this. So this is population, this is time. So you'll notice that we start concave up, and then as we start increasing, we turn and we become concave down. And as we go up, we eventually reach this high point where we level off. And so that point we reach is our L. That's our carrying capacity. That is the maximum population. And once we reach that, we stay at that maximum population. Okay, so that's L. That's how we go there. Our growth rate K is going to impact how quickly we get there. So if our K was a little bit larger, our model might look like this, right? It might go there faster, right? So if K is bigger, it goes up faster. But we have this special point on our logistic growth model, and it's called the point of diminishing returns, okay? And so I want to point out why this point is important and what we know about it. So I want you to consider the rate at which our population is growing, okay? So we're talking about derivatives. So if we look at these tangent lines, what I want you to notice is that at the point of diminishing returns is when this tangent line is the steepest, okay? So we have the steepest tangent line. And what that tells us is this is where the population is growing most rapidly. Okay, so there's a lot of merit in knowing when your population is growing the fastest. That helps us sort of understand a lot of things biologically about our population. And so it turns out that this inflection point, okay, is going to happen when our population is exactly half of the carrying capacity. Okay, so if the maximum population is 500, then this would happen when the population reaches 250, right? So it's when it's half of the maximum. Now, this is helpful for us because if we can figure out that a population is growing most rapidly, then we can predict how big the population will be. So what does that look like in practice, right? So let's say we're measuring penguins on an island, right? And biologists go back every year. They're looking at the rate of change. So how many new penguins do we get each year, right? And so let's say the first year there's 5 new penguins. The next year there's 10 new penguins. The next year there's 20 new penguins, right? So we're seeing that we're getting more and more and the rate is increasing. But let's say one year there's slightly less. Now there's only 16 penguins. Well, that means that the rate has started to slow down, right? So we can look at the population for when the rate was the largest, and we can double that to know how big the population can become, right? So this, again, is really helpful for predictability. So if we're modeling things in real time, as soon as we see that rate slow down, we know that we've just passed this important point, which is the point of diminishing returns. And that helps us, again, to predict the maximum population. So as you can imagine, we would like to know when this happens. We know it happens when the population is L/2, but what about the time, right? So this is the population size, but what about the time? So consider this. Let's say we have our generic model, L/1 plus CE to the negative KT. And we know that the point of diminishing returns happens at L/2 when we're half the population size, okay? What that means, since our numerators are the same, is that if we wanted to know when that happened, we could solve for T generically by setting our denominators equal. We have 1 plus CE to the negative KT equals 2, okay? So what I would like you to do is I would like you to take 2 minutes and see if you can algebraically solve this for T. Remember, T is our independent variable, so that's what we're solving for, and that will allow us to have a formula for when we reach the point of diminishing returns. Okay, so think about what you know about algebra and the rules about how we solve for these things and see if you can solve for T. So take, again, about 2 minutes and then we'll go through that together. All right, take about 30 more seconds. All right, so let's look at the algebra on this and make sure we can see where this formula is going to come from. So we want to isolate the term with the variable in it. So the first thing we do is subtract 1 from both sides. when we do that, on the left, we're left with CE to the negative KT. And if we subtract 1 from the right, we have a 1. Now, again, we're trying to isolate the term, so we're going to divide out that C. So we have e to the negative KT equals 1 over C. Now we can take natural logs of both sides. Remember, if you take the natural log of one side, you have to take the natural log of both sides. So the natural log of e to the negative KT equals the natural log of 1 over C. Now, again, we take the natural log because now that power can come down out front. So negative KT equals the natural log of 1 over C. Again, when this comes down out front, we're left with the natural log of E, which is 1. So anything times 1 is just itself. So now we finally solve for T, and we get the natural log of 1 over C divided by negative K. Okay, so notice that the negative here is from the negative that was in the model. So we don't need to cancel it out. And we'll see how this works in application in some examples we do in a few minutes. But here, this is the natural log of 1 over C divided by negative K. So how might we ask about this particular point? Often the question is phrased as, when is the population growing most rapidly? When is it growing fastest? When is it growing quickest? Or any other verb that indicates that this is the fastest point in time. So this particular calculation answers the question when, right? Because it's a time. When is the population growing the most rapidly, right? This L over 2 answers the question, what is the population when it's growing most rapidly, right? So if we're looking for the actual population size, that's when we use L over 2. We use this much more often, right? When is it growing most rapidly? And again, these C and K are going to be given in the model. So these are numbers you're going to plug in order to get that particular time. Time should be positive. If it's not, you lost a negative somewhere along the way. Okay, so let's go ahead and look at sort of an example that encapsulates all the types of questions we ask about logistic growth models. All right, so this says, suppose a population can be modeled by P of T equals 200 over 1 plus 39 e to the negative 0.2 t. So you may not be able to see the decimal point here, but there is a 0.2 t. You know what? I'll actually write this just a little bit bigger. Just to make sure we can see that decimal point. Okay. Where P of T is in thousands of people. So any population that you were to talk about would be in thousands. And time is in years since 2000. So this is when the model started in the year 2000. So if you were to solve something and you got T equals 3, that would correlate to the year 2003, right? So we have to add it back to the year 2000. So these are the 4 common questions that we ask when we talk about logistic growth models. So I'm going to have you try these and see which ones you can figure out. Okay. B and C we talked about explicitly a minute ago. A is sort of an algebra situation. What does it mean to be the initial population? Think if you remember what that might mean. And for part D, when will this population reach 150? Well, you will have to set your model equal to 150 and use algebra to solve for T. Okay, so these are the 4 sort of quintessential questions. I'm going to have you try them out, see what you can come up with. I'll give you about, I don't know, 5 minutes. The last computation, part D, is a little bit long, so try to be really careful with your algebra. Okay, so take 5 minutes, work out these parts of the problem, and then we'll go through it together. All right, take about 30 more seconds. All right, so let's go through each of these questions. So the first question is, what is the initial population of this model? So when we see the word initial, right, that tells us that we are wondering what's happening at time equals 0, right? So we have this population that's modeled. And so we want to know what's happening right at the beginning. So if we are trying to figure out the initial population, we're going to plug in the 0 for t. Okay, so remember, if you have something raised to the 0, so this is going to end up being e to the 0. Anything to the 0 power is going to be 1. Okay, so this is going to be 200 over 1 plus 39. We know 1 plus 39 is 40. Okay, so we have 200 over 40, which is going to give us an initial population of 5. Now, if we're talking about this, remember population is in thousands. So that means that whatever we're modeling, we start with 5,000 of them, right? Because that 5 has the units of thousands. This is something that often comes up if you are trying to solve for C. Okay, so we have the 39 here, but sometimes you don't, and it'll say something like, you know, the initial population is 5. And so you have to remember that initial population is time equals 0. And then you'd put in a 5 for the initial population, and then you solve for C. Okay, so again, if you didn't remember that initial population translates into time equals 0, you may want to make a little note so that if it comes up again, you remember that that's part of what we're solving. Part B, what is the carrying capacity of this model? So that's the maximum population. And again, that number comes right from the top. So here we have 200, and again, the population's in thousands. So we can either write it as 200,000, or we could say 200,000. That is the carrying capacity of this model. So 200 is really the number we need to take from our model to answer this question. Part C, when is this population growing most rapidly? So now this is where our formula comes in. So we said that this happens when you do the natural log of 1 over c divided by negative k. Okay, that's when the population is growing most rapidly. That's the point of diminishing returns. So we need to apply the values from here. So we have the natural log of 1 over 39 divided by negative 0.2. Okay, this is the exact time. Usually we're going to crunch this down into a decimal to get the numerical representation, but if for some reason you need it as an exact time, you would enter it like that, okay? But when you crunch this down into a number, we're going to get 23.8 when you round to 1 decimal place. So this means that 23.8 years after we started modeling it is when we're growing most rapidly. But what I want to remind you is time is in years since 2000. So here it's growing most rapidly during 2023, right? So 2023 is the year. We're partway through that year, right? We added that on to the year 2000. Finally, the last question asks, when will this population reach 150? So here we have to do some extra calculations in order to solve algebraically. So I'm going to grab a piece of blank paper. Maybe. All right, we're going to need some space here. Okay, so we want to take this 150 and set it equal to our model, which is 200 over 1 plus 39e to the negative 0.2t. And I'm going to remind you that the 150 is actually 150 over 1. Okay, so what we can do is we can do some cross multiplication here. Hopefully that sounds familiar from algebra, where we're going to bring this term to the top left and this term down to the bottom. So we have 1 plus 39e to the negative 0.2t over 1 equals 200 over 150. I cross multiplied and simplified that way because I'm trying to get the t out of the denominator. Okay. So here on the left, anything over 1 is just itself. And I have the t out of the denominator. And on the right, I can simplify by dividing the top and the bottom by 50. So this is just 4/3. I strongly encourage you to keep things in fractions and not turn them into decimals, because often you have to find an exact solution. And if you turn things into decimals, it turns them into approximations. So now we're going to subtract 1 from both sides. So we get 39e to the negative 0.2t equals 1/3, because 4/3 minus 1 is 1/3. Now we're going to divide both sides by 39. So we have e to the negative 0.2t equals 1 over. Now, since we're dividing 39 over, we would multiply the 3 by 39 to keep it as a fraction. So 1 over 117. Now we can take the natural log of both sides. Okay, and again, we want to do that so we can get the power to come down. The natural log of e is just 1, so that disappears because anything times 1 is itself. So t, finally, we're going to divide both sides by this negative 0.2. So t is the natural log of 1 over 117 divided by negative 0.2. So this is an exact answer. But I'd say half the time you're going to be asked to round to a particular decimal point. So let's say, oh, you guys, this one is 23.8. I looked too quickly at my paper. So let's go back for a second. So here for part C, we need to make a correction, okay, before we move on. So for part C, this was 18.3. I looked at the wrong answer when I was copying it over. This is happening during 2018. So make that correction for part C. And then part D is where when you do this calculation, you get 23.8. So that happens in 2023. Okay. So again, I'd say about half the time you are asked for an exact answer, which means you would need to enter it like this with the natural log in it. The other half of the time, you'll be asked to round to the nearest decimal. And so then you would plug this into your calculator to get the numerical translation of time. Okay. So again, just as a correction, part C, this is all right. But when you plug it in, you get 18.32. And for part D, when you plug it in is when you get 23.8. Okay. So those are the 4 common questions that come up with natural logs, logistic growth models. So these are the types of things that you can expect that you'll be doing on homework. or on the mini quiz or things like that in terms of application. So things related to these types of questions. These are the common questions. There's one other type of question that comes up that's slightly different, where we're going to use the idea of logistic growth models to talk about business or something else. And the way that comes up is through tables. So let's look at the second example here. So sales projections often follow logistic growth curves, right? So if we're talking about selling something and we're in the business of selling something and we want to predict how much we will sell, that often happens logistically. As you can imagine, once you reach some sort of saturation of sales, you kind of stay there after the item has, stopped being popular. So suppose the table below tracks the sales of a new book since it was released, and the data is logistic. So that means it follows a logistic growth pattern, okay? Part A, determine the most likely place that this function has an inflection point. All right, so how did we do that? So just as a reminder, this goes back to chapter 2 and a little bit in chapter 3, where in order to look at data on a table and talk about inflection points, we need to approach the first derivative for every point on the table. And once we have the first derivative, we can look at the behavior of that to make a pretty solid guess where we would have an inflection point on the second derivative. Then once we've identified that point, we want to use that answer to predict the maximum potential sales for the book. The way that we're going to think about that is by remembering, I'm going to bring back this picture for a second, that at the inflection point is when we are at half the maximum population. So if we can figure out where that inflection point is, we can double the dependent value to figure out the maximum sales. Okay, so what we're going to do is we're going to try it out. Hopefully you remember how to approximate the first derivative on the table. That's sort of the first step for part A. And then you can figure out the inflection point. And then hopefully we can connect that here in part B to figure out maximum sales. Okay, so I'm going to give you about 2-3 minutes. Again, the first step is to sketch out an approximation for the first derivative at every point. And then you can start to answer the questions. Okay, so take about 3 minutes and then we'll go through it together. All right, take about 30 more seconds. All right. So again, in order to figure out where the inflection point is, we need to have some information about the second derivative. And the only way to get information about the second derivative is to have some information about the first derivative. So we're going to approximate the derivative down the table. So again, when we're at the end points, we're using the point right next to it. We're doing change in y over change in x. So 4 minus 2 divided by 2 minus 0, that's going to give us a rate of change of 1. For the next point, we're going to use the 2 points around it. So 12 minus 2 divided by 4 minus 0. So 12 minus 2 is 10 divided by 4 will give me a 2.5. And then we're going to continue doing that down the table. So the next one will be 6.5, 77 minus 12 divided by 8 minus 4. I got 16.25. 107 minus 30 divided by 10 minus 6. I get 19.25. 120 minus 77 over 12 minus 8. That's going to give me 10.75. And then finally, 120 minus 107 divided by 12 minus 10 gives me 6.5. So once we have an approximation of our first derivative, what we want to look for is where our first derivative is increasing and decreasing. So 1, 2, 6.5, 16.25, 19.25. That's all increasing. But then after that, we see that we go 19.25, 10.75, 16.5. So that's decreasing, right? And so when our first derivative is increasing, our second derivative is positive. When our first derivative is decreasing, our second derivative is negative. And it's the point that we change from increasing to decreasing where the second derivative is most likely to be 0, right? And that is where we have inflection points. So here, this point right here, 8,77, is the most likely place that this function has an inflection point. Okay, so at 8 months, the sales are 77,000. And that is when things are changing. That's when we are sort of at the peak rate, but then we're slowing down. So for part B, use your answer to predict the maximum potential sales for this book, right? So if this is our inflection point, we know that the dependent value of 77, right, is going to be exactly half of the maximum. Right? So again, that relates back to our inflection points. So what we need to do is we need to double that number to figure out what our maximum will be. So 77 times 2 is going to give me 154,000 is the prediction for the maximum potential sales. That's what the carrying capacity is going to be. So this is sort of an application of an application, right? So logistic growth models in general are biology applications using maxes, mins, inflection points. But we also see these trends in sales where things grow logistically. So we're able to use what we can with our analysis to make predictions about any types of sales by locating inflection points and then doubling, right, the amount to think about what the maximum may be. So that's sort of the other alternate application we'll be seeing. All right. So now we're going to look at another application that's paired with logistic growth models, but sort of a different type of application. So this is our third type, and this comes from medicine and chemistry. And this is called surge functions. So first, I'm going to take a minute to talk about what surge functions are and why we would be interested in modeling them. So when you talk about going into medicine or thinking about the chemistry within the body, surge functions model what happens when you take some sort of medication. Okay, so let's say you have a headache and you take an Advil, right? We want to know how much of that drug is in your body at any given time and how long it takes your body to process it and sort of get rid of it over time, right? So that's what surge functions are looking like. When things are ingested into the bloodstream, how long does it stay there? When is it sort of peaked in your bloodstream? And when does it leave the body? Okay, so that's the idea of surge functions. And surge functions have this general model. I'm going to write it a little bit bigger. A, T, E to the B, T. So C is for concentration. Okay, and it's the concentration of a drug in the bloodstream. Now, A and B are going to be constants that depend on the drug that you're modeling. And T is time, and T is our independent variable. Okay, so let's start by looking at a picture of a surge function. So as we see here, surge functions start at time equals 0. So if you were to take an Advil and I were to draw your blood immediately after you took it, there wouldn't be any Advil in your bloodstream at time equals 0. It takes a minute for your body to digest it and for it to start being released. So over time, the amount of drug increases until it reaches its maximum potency in your bloodstream. That's when you have maximum efficacy for whatever the drug is. And then it slowly starts to trickle back out of your body, right? So you don't have Advil in your body forever. It slowly trickles out until it's completely removed. So what I want to mention here and what I want you to notice is that there's two important things that we've been studying, which is maximum. We see that there's a maximum concentration. And then there's also an inflection point here, right? So we're concave down, and then we kind of turn around, and it slowly comes out here. And what I want to mention is oftentimes in medicine, that inflection point is when you want to recommend taking a second dose, right? And so, for like an Advil, I think it's like every 4 to 6 hours. So this inflection point for most people would probably be around hour 5. So you get like this little window, because once we get to that inflection point, it's not really working that much anymore. And it's just sort of dissipating out of your body. So some people obviously don't need a second dose, but if you do, that's when it's safe to take it, because the rate at which you are dissipating is pretty similar to the rate at which it starts to go back up, so that you don't overdose and go too high. So that's why the inflection point becomes important. So the two things we're going to be interested in are, when does the maximum occur and when does the inflection point occur, right? And these are things we've been talking about in chapter 4. So for maximums, we can see that this is at a critical point. We have a horizontal tangent line there. So what we can do is we can take the original model and take the first derivative, set it equal to 0, and figure out where does the inflection point, or where does the maximum happen, the critical point. So again, the model that we started with, C of t equals a t e to the bt. Okay, so the first thing we're going to do is we're going to try to find the first derivative of this function and figure out what is the critical point. So once you find the first derivative of our function, you're going to set it equal to 0 and try to solve for t. Now remember that a and b are constants. And what I want to point out here is when you find the first derivative, you're going to need to use a product rule, right? Because there's a t here and there's a t here. So I'm going to give you about, 2 minutes to see if you can figure out what the first derivative of this function is using the product rule. Again, a and b are constants. And if you still have time after that comes up, see if you can set it equal to 0 and solve for t, because that's going to give us when this maximum happens. Okay, so take about 2 minutes, try to work it out, and then we will go through it together. All right, take about 30 more seconds. All right. So again, in order to find the first derivative of this function, we're going to have to do a product rule. So here, the first function is at. The second function is e to the bt. We need to find each of their respective derivatives. And so for at, remember t is your variable and a is a constant. So the derivative is a. And for e to the bt, remember a b comes out. So we have be to the bt. Okay. So now the product rule says we're going to do f prime times g plus g prime times f. So f prime times g, we have a e b e to the bt plus f prime times g, which is a e to the bt. Okay. So what we need to do now is we need to ask the question, when does that equal 0? Right? Because we're trying to find the critical points here. So what we're going to do is we're going to factor out the e term. So we have e to the bt. So from the first term, we're left with a times t times b. Plus, from the second term, we're left with an a. Now, remember from algebra that e to the bt will never equal 0, right? So there's no value we can plug in here that'll make that equal to 0. So we need to just consider what's inside the parentheses, okay? So we have a times t times b plus a equals 0. Now remember, t is our variable. That's what we're trying to solve for. So we're going to subtract this a to the other side. We have a times t times b equals negative a. So to get t alone, we have to divide out the a and the b. And we get t equals, so over here, the a's will cancel. And we get negative 1 over b. So that means that the maximum, so notice there's only one critical point, so we know it's got to be this one. The maximum happens at -1 over b. So once we have a model with values in it, we're going to take the value that's up here in the power, and we do -1 over b to answer the question, when does the maximum occur? Okay, so we want to do something similar for the inflection point. We want to see if there's a common way for us to solve in general for when the inflection point happens. So the next thing we're going to do is we're going to try to figure out, when does the second derivative equal 0? So as a reminder, this was our unfactored first derivative. So we want to take the derivative of that to find the second derivative. Okay, so for the first term, you're going to have to do another product rule. And I would recommend putting a, t, and b together, and then e to the bt is your second function. And then for the second term, you can just take the derivative of this without doing a product rule, because there's only one t. Okay, so I'm going to give you another 2 minutes to find the second derivative of this function. And if you finish that and still have time, you can try to answer the question, when does the second derivative equal 0? Okay, so again, this is good practice on our derivatives that we've been doing. This one's a little tricky algebraically, so just be careful, but take about 2 minutes and see if you can figure out the second derivative and where the second derivative might equal 0. And then we'll go through it together. All right, take about 30 more seconds. All right, so let's take a look at the second derivative here. We're going to need some extra writing space. So as a reminder, first derivative, we have a times t times b e to the bt plus a e to the bt. That was our first derivative. And we want to find our second derivative here. Okay, so again, for the first term, we have to use a product rule because we have two t's in here. So we have two terms that are multiplied together. So here for f, I'm going to use a times t times b. And for my g, I'm going to have e to the bt. So when I take the derivative of a times t times b, a and b are constants. If you have a constant times t, the derivative is just that constant. So you get ab. And the derivative of e to the bt is be to the bt. So we have f prime times g prime times f. So we have ab e to the bt plus, now we have an a and a t and a b times be to the bt. So there's another b, so I'm going to make that b squared. Okay, so that's the derivative of the first term. We still have to take the derivative of the second term. And so here the a is a constant multiple and a b comes out from taking the derivative. So that's the derivative of that last term. Notice that the first term and the last term are the same. So we can simplify a little and combine them. So we have 2ab e to the bt plus a times t times b squared e to the bt. That's what our second derivative looks like. And again, since we're looking for inflection points, we want to know when does that equal 0. If we factor out the e term, we're left with 2ab plus a times t times b squared equals 0. Again, the e term, e to the bt, that will never equal 0. So we just need to consider what's in our parentheses. So 2ab plus a times t times b squared equals 0. Let's subtract the 2ab to the other side. So we have a times t times b squared equals negative 2ab. Again, t is the variable we're solving for. So we divide both sides by ab squared, and we get t equals, so those a's will cancel, this b will cancel with one of these b's, and we end with negative 2 over b. So the question about when do we get to the inflection point is answered by finding the generic inflection point, which happens at negative 2 over b. Okay, so now we know the maximum happens at negative 1 over b, and the inflection point happens at negative 2 over b. So let's go ahead and look at sort of the common examples of what we will ask and see if we can apply what we just figured out to our example here. Okay. So example 1 says the amount of a particular drug in the bloodstream measured by C of t equals 5t e to the negative 0.25t. So there is a decimal point there in front of the 0.25, measured in milligrams, and time t is measured in hours since the drug has been administered. The question is, what is the maximum concentration that this drug reaches? So we are actually looking for the concentration here, the dependent value. But in order to find that, we first need to determine when the maximum happens. So I'm going to give you 2 minutes. And what you need to do is first figure out when it happens in terms of time. You can use this formula or you can do the derivative out. And then you need to plug that value back into the original function to get the corresponding concentration. Okay, so I want you to think about things like units, see what you can figure out. So take 2 minutes and then we will go through this together. Okay, take about 30 more seconds. All right. So in order to answer the question, what is the maximum concentration, we actually have to start with when does the maximum concentration occur? And that's our formula here at time equals -1/b. And so here we have to go to our particular formula given here and plug in our b. So the b here is the number up here in the power. So it's -0.25. The negatives will cancel. We will get time equals 4. So 4 hours. So the maximum will occur after 4 hours. What is the maximum? Well, then we need to take that 4 when it happens and plug it into the concentration function to figure out what the concentration is at that time. So we have 5 times 4, e to the -0.25 times 4. We would then plug that into the calculator and we get 7.358 when you round to 3 decimal places, and the concentration is in milligrams. Okay, so the two most common questions are when does the maximum happen? And that's the time. And what is the maximum concentration? That's when you have to plug that back into the function. Okay. Now, the second type of question that comes up is a little more tricky because the algebra on it doesn't quite work out as easily as this type of problem. So the second type is when we have something like this. The concentration in nanograms per milliliter of a particular type of medicine in the bloodstream is given in the graph below, and I'll show you in a minute the graph, as a function of time t in hours. If the minimum effective concentration is 10 ng per ml, at approximately what time does the effect of the medicine wear off? Okay, so if you are given what's called a minimum effective concentration, like here, what's going to happen is we are trying to figure out where this number intersects with our function. Okay, so the picture looks like this that we're looking at here. Sometimes you're given the function algebraically, like we were in example 1, and sometimes you have a picture, but we're trying to figure out when we fall below 10 ngs per ml. So we would need to go to 10, and we would need to figure out where those intersections happen to figure out when the medicine wears off. So it intersects in 2 places. Okay, the first one, I don't know, is approximately 1, and the second one is time equals 10. Since we are trying to figure out when the medicine wears off, we are looking for the later intersection point. Okay, so this is where it wears off, and this is where it kicks in. Right, so this is when you can start feeling the effect, because the minimum effective concentration means that it's only working when you are above. Now, one thing I want to caution you about, if you are given a concentration, like say, you have 10t e to the -0.3t, and you're told that the minimum effective concentration is, I don't know, 20, okay? What you would need to do in order to figure out when you fall below the minimum effective concentration is you would need to graph the original function, and you would also need to graph y equals 20, and you would need to either eyeball or trace the graph to figure out the intersection point, because 1, it doesn't always happen at the inflection point. So unless you are asked specifically for the inflection point, you have to graph it. 2, if you try to set them equal to solve, you don't have the skills to solve that. That's not an easy algebraic problem, and you won't be able to figure it out by hand algebraically. So the only way to do this is to graph the function, graph the line like we did here, and then identify the intersection point. Okay, otherwise you're not going to be able to figure it out. You could theoretically guess and check, but that's also not as effective of a method as graphing it. Okay, so here with this type of work, we're using, graphs of the picture. We're using the formulas that we have here to answer any of our questions. So again, this is sort of the common question, example 1. When and what is the maximum concentration? But there's certainly other questions that could come up. But if they do, what you'll need to solve them is these formulas here and the ability to graph and find intersection points. Okay, so that's the end of surge functions. So we'll stop here. On Thursday, we're going to start chapter 5. And so we'll just sort of plug along. Have an excellent rest of your day, and I will see you all on Thursday.